Close your eyes for a second. Picture space. What do you see? Probably blackness, right? Empty void. Maybe some stars scattered around. Planets floating in the distance. That's what most people imagine when they think of space. A big empty container where things exist. And that makes sense. That's what it looks like in photos. That's what we call it. Space. Empty space. Outer space. The vacuum of space. The language itself tells you it's nothing. Just emptiness where occasionally something interesting happens. A star here, a planet there. But mostly nothing. And if that's what you think space is, I need to tell you something. You're completely wrong. Not a little wrong. Not technically wrong, but close enough. Fundamentally, deeply wrong. And Carl Sagan spent his entire career trying to show people just how wrong this simple assumption is. Because space isn't empty. It's not a container. It's not a stage where the universe performs. Space is something. Something real, something physical, something that bends and twists and vibrates. And once you understand what space actually is, once you see it the way Sagan saw it, everything changes. The universe stops being a collection of objects floating in nothing and becomes something much stranger, much more connected, much more alive. Let me show you what I mean. Let's start with something simple, something you think you understand. Distance. You know what distance is, right? The space between 2 points, the gap between here and there. If I ask you how far away something is, you can tell me 10 feet, 100 miles. Simple, measurable, obvious. Except in space, distance doesn't work the way you think it does. And this is where your intuition starts to fail you. Because the distances in space are so vast, so incomprehensibly large, that using normal units like miles or kilometers becomes meaningless. They don't convey the reality of what you're talking about. Let me give you an example. The nearest star to Earth after the Sun is called Proxima Centauri. It's 4.24 light years away. You've probably heard that number before. 4.24 light years. Sounds manageable, doesn't it? Just over 4. Not too bad. But let me translate that into something you can actually grasp. A light year is the distance light travels in 1 year. And light is fast, really fast. It moves at 186,000 miles per second. In the time it takes you to say the word second, light has traveled far enough to circle the Earth 7 times. That's how fast light is. And in 1 year, traveling at that speed, light covers about 6 trillion miles. 6 trillion. That's a 6 with 12 zeros after it. And Proxima Centauri is 4.24 times that distance away. That's 25 trillion miles. 25 trillion. And that's the closest star. The nearest neighbor we have after the Sunday. Now, let me put that in perspective. The fastest spacecraft humans have ever built is Voyager 1. It's currently traveling at about 38,000 miles per hour. That's fast by human standards, really fast. But if Voyager 1 were headed toward Proxima Centauri, which it's not, it would take about 75,000 years to get there. 75,000 years. That's longer than recorded human history. That's longer than modern humans have existed as a species. And that's to reach the nearest star. Not a distant galaxy, not the edge of the universe. The nearest star, the one that's practically in our backyard in cosmic terms. So when you think about space, when you picture the distance between things, you're probably thinking too small, way too small. Your brain can't really process these numbers. They're too big. They don't fit into human experience. We evolved to understand distances we can walk, distances we can see, miles, maybe hundreds of miles. But trillions? Your brain just gives up. It hears the number and files it away as really far without actually comprehending what it means. And this is the first way space breaks your understanding. The scale, the sheer incomprehensible scale of it. But let's go deeper, because distance isn't even the strangest part. Let's talk about what's between those distances. Let's talk about what space itself actually is. You think it's nothing, right? Empty void. But here's where Carl Sagan would stop you. Space is not nothing. It's a thing, a physical thing. We call it space-time. And it has properties. It can bend. It can stretch. It can vibrate like a drum. And understanding this, really understanding this, changes everything. Here's how we know space is something. Einstein figured this out with his theory of general relativity. He showed that massive objects, things like stars and planets, they bend space around them. Imagine a trampoline. Now imagine you place a bowling ball in the center. The trampoline sinks down, right? It creates a depression, a curve. Now, if you roll a marble across that trampoline, it won't travel in a straight line. It'll curve toward the bowling ball because the surface itself is curved. That's what mass does to space. It bends it, and when space is bent, things moving through that space follow the curves. We call that gravity. But gravity isn't a force pulling things together. It's objects following the curved geometry of space itself. Think about what that means. Space, the thing you thought was empty, has geometry. It has shape. It can be curved by mass. And that curvature is what keeps the Earth orbiting the Sunday. It's what keeps you stuck to the ground. It's not some invisible force reaching out and pulling. It's the shape of space itself. And when you realize that, when you really absorb it, you start to see that space isn't a backdrop. It's a participant. It's part of the system. The universe isn't objects in space. The universe is objects in space together, interacting, shaping each other. But there's more, and this is where it gets really strange. Space can also stretch, not metaphorically, actually stretch, like pulling on a rubber band. And it's stretching right now. The universe is expanding. Galaxies are moving away from each other because the space between them is growing. New space is being created. Not matter moving through space, space itself expanding. And this happens everywhere, between galaxies, between stars, even between you and the screen you're reading this on. Space is expanding. It's just that on small scales, other forces like gravity and electromagnetism are stronger, so they hold things together. But on cosmic scales, where gravity is too weak to hold distant galaxies together, the expansion wins, and galaxies drift apart. Now, if space is expanding, that means it used to be smaller. Wind the clock back far enough, and all the space in the universe was compressed into an infinitesimally small point. That's the Big Bang. Not an explosion in space, an explosion of space. Space itself expanding from a point into everything we see today. And here's the part that should make your head hurt. If space itself began with the Big Bang, if space is expanding from that initial point, then asking what's outside the universe, what's beyond space, that question doesn't make sense. There is no outside. There is no beyond. Space is all there is. It's not in something. It is the something. Carl Sagan loved this idea. He loved showing people that the universe is stranger than their intuitions suggest. That the comfortable, common sense view of reality, the one where space is just empty and objects move through it, that view is wrong. And being wrong about something this fundamental means you're wrong about a lot of other things too. Let's talk about another assumption you probably have. You think you know what now means. Right now, this moment, the present. It's happening right now all over the universe, right? Wrong. There is no universal now. Time doesn't work that way. This is another thing Einstein figured out. Time is relative. It depends on how fast you're moving and how strong the gravity is where you are. Two events that are simultaneous for you might not be simultaneous for someone moving at a different speed. Time literally runs at different rates depending on your motion and your position in a gravitational field. Here's an example. Astronauts on the International Space Station are moving very fast relative to people on Earth. Not anywhere close to the speed of light, but fast enough that time dilation effects are measurable. Their clocks run slightly slower than clocks on the ground. Not by much, fractions of a second over months, but measurably slower. If you took an identical twin, sent one to the space station for a year while the other stayed on Earth, the one in space would age slightly less. Not enough to notice by looking, but enough to measure with atomic clocks. Time itself is running at a different rate for them. They're not experiencing the same now you are. Their present is different from yours. And it gets weirder. Gravity also affects time. The stronger the gravity, the slower time runs. If you're standing on the surface of a massive planet, time runs slower for you than for someone orbiting far above. This isn't speculation. This is measured fact. GPS satellites have to account for this. They're farther from Earth's center of gravity than you are, so time runs slightly faster for them. If the GPS system didn't correct for this time dilation, your navigation would be off by miles within a few hours. We have to account for Einstein's relativity just to get directions to the grocery store. That's how real this is. So when you think about space, when you imagine the universe, you probably imagine everything happening now, all the stars and galaxies existing in the present moment. But there is no single present moment. There's no cosmic clock ticking away the same time everywhere. Time is local, it's relative, it's woven into space itself. That's why we call it space-time. Not space and time, space-time. One thing, and that thing is bendable, stretchable, and relative. Now let's talk about what's in this space. Because even though space isn't empty in the way you thought, you probably still think that between objects, between stars and planets, there's mostly nothing, a vacuum. And that's true in one sense. There's no air, no matter you can touch. But the vacuum of space is not empty, not even close. And this is where quantum mechanics comes in and makes everything even stranger. At the quantum level, at the scale of atoms and subatomic particles, space is not calm, it's not quiet, it's churning constantly. Particles pop into existence out of nowhere, exist for a brief instant, and then disappear. We call them virtual particles. They're real enough to have measurable effects, but they don't last long. They borrow energy from the vacuum, exist for a tiny fraction of a second, and then annihilate, paying the energy back. This happens everywhere, all the time. In the space between your atoms, in the space between stars, the vacuum is seething with activity, with potential, with energy. There's even a field that fills all of space, the Higgs field. It's what gives particles mass. Without the Higgs field, particles like electrons and quarks would be massless. They'd zip around at the speed of light and couldn't form atoms, couldn't form you. The Higgs field is everywhere. It's part of the fabric of space itself. And particles interact with it. And that interaction gives them mass. You have mass because you're moving through the Higgs field right now. Space isn't empty. It's full of fields, full of potential energy, full of virtual particles flickering in and out of existence. Carl Sagan understood that this was hard to grasp. He knew that people's everyday experience tells them space is empty. You look up at the night sky and you see blackness. You see gaps between stars. And your brain says, that's nothing, that's empty. But Sagan would tell you to look closer, to think harder. Because what you're calling nothing is actually a dynamic, active, structured medium. It has properties. It follows rules. It does things. And ignoring that, thinking of space as just absence, that's like looking at a calm ocean and thinking water is nothing because you can't see the waves. Let me tell you about something else you probably think you understand. You think the universe is old. You've heard that it's about 13.8 billion years old, and that sounds ancient, incomprehensibly old. And it is. But here's what you might not realize. That age, 13.8 billion years, that's how long ago the Big Bang happened in our reference frame. But the universe doesn't have a single age everywhere. Because of time dilation, because time runs at different rates in different places, the age of the universe is relative. An observer moving at a different speed or in a different gravitational field would measure a different age. Not by much, but different. And here's another thing. When you look out into space, you're looking back in time. Light has a finite speed. It takes time to get from there to here. When you look at the sun, you're seeing it as it was 8 minutes ago because that's how long it takes light from the sun to reach Earth. When you look at the nearest star, Proxima Centauri, you're seeing it as it was 4.24 years ago. When you look at the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago. The farther you look, the farther back in time you see. And when astronomers look at the most distant galaxies, they're seeing them as they were over 13 billion years ago. They're seeing light that's been traveling for almost the entire age of the universe. Those galaxies might not even exist anymore. They might have changed completely, or been destroyed, or merged with other galaxies. But we won't know for billions of years because the light from their present hasn't reached us yet. So when you look up at the night sky, you're not seeing the universe as it is now. You're seeing a patchwork of different times. Each star, each galaxy, is a different moment in the past. The universe you see is a time machine, a fossil record, a history book written in light. And that means the present, the now you think you're experiencing, is a constructed thing, a slice through space-time that's unique to you, to your speed, to your position. Someone else, somewhere else, is experiencing a different now. And both of you are right. Carl Sagan spent a lot of time thinking about this, about how our intuitions fail us when we try to understand the cosmos, about how the universe is fundamentally stranger than it seems. And he realized that this strangeness isn't a bug, it's a feature. It's telling us something profound. It's telling us that reality doesn't conform to human expectations, that the universe wasn't made for us to understand easily, that we're a species that evolved on a small planet dealing with medium-sized objects at medium speeds, and our brains are optimized for that, not for black holes, not for quantum mechanics, not for space-time curvature, relativistic effects, or the vast scales of the cosmos. And yet, despite that, despite our brains being so poorly equipped for this, we can understand it. Not intuitively, not easily, but through science, through mathematics, through careful observation and rigorous thinking, we can figure it out. We can build models that work, that make predictions. That let us navigate by satellite and communicate across continents and send probes to distant planets. We can know things that our senses don't tell us. We can see past our intuitions to the reality underneath. That's what Sagan found so beautiful. Not that the universe is easy to understand, but that it's hard, and we can do it anyway. That we're these tiny creatures on a tiny planet, and we've figured out the age of the universe. We've mapped the curvature of space-time. We've detected gravitational waves. We've seen atoms. We've split them apart and seen what's inside. We've looked back to the beginning of time. And none of it is obvious. None of it matches our everyday experience. All of it required us to question our assumptions, to challenge what we thought we knew, to be wrong over and over, and then find better answers. Let me give you another example of how space breaks your intuitions. You think objects in space are far apart, right? Isolated. Stars separated by light years. Galaxies separated by millions of light years. And that's true in one sense. The distances are enormous. But in another sense, everything in the universe is connected, not metaphorically, physically connected, through space-time, through gravitational fields, through the quantum fields that permeate everything. When the sun moves, it doesn't just move through space. It drags space with it. It creates ripples in space-time that propagate outward at the speed of light. When two black holes collide billions of light years away, they send gravitational waves through space-time, and those waves eventually reach Earth. We've detected them. We've measured them. The fabric of space itself is vibrating from events that happened unimaginably far away and long ago. Everything that has mass, everything that has energy, is constantly interacting with space-time, bending it, shaping it, sending ripples through it, and those ripples connect everything to everything else. This is what Einstein called spooky action at a distance, though he was referring to quantum entanglement. But the principle is the same. The universe is not a collection of isolated objects. It's a web, a network, everything touching everything else through the medium of space and the fields that fill it. You are not separate from the cosmos. You're embedded in it, part of it. And everything you do, every motion you make, sends tiny ripples through space-time, imperceptibly small, but real. You're constantly interacting with the entire universe, and the universe is interacting with you. Carl Sagan loved this idea, this sense of connection, of being part of something vast. He talked about it all the time, how we're made of star stuff, how the atoms in our bodies were forged in the cores of ancient stars that exploded and scattered their material across space. how the calcium in our bones, the iron in our blood, the carbon in our cells, all of it came from stars. We are literally made of the universe. We're not in the universe. We are the universe. A small part of it that's become conscious, that's become aware of itself. And that awareness, that ability to look out and ask questions, that's rare, maybe incredibly rare. Maybe we're the only ones in this galaxy who can do it. And if that's true, then we have a responsibility, not to some external authority, to the cosmos itself, to not waste this opportunity, to keep learning, to keep asking, to keep challenging our assumptions and discovering new truths. So when I say you don't understand space, I don't mean it as an insult. I mean it as an invitation to look closer, to think deeper, to question what seems obvious. Because space is not what it seems. It's not empty. It's not a stage. It's not even really separate from time. Space is a thing, a strange, dynamic, connected thing that bends and stretches and vibrates. And understanding that, really understanding it, changes how you see everything. The distances that seemed impossibly large, they're not just distances. They're measures of space-time curvature. The emptiness you thought existed between objects, it's not empty. It's full of fields and virtual particles and potential energy. The present moment you thought was universal. It's not. It's local and relative. The isolation you thought separated objects, it doesn't. Everything is connected through the fabric of space-time itself. And here's the thing Carl Sagan would want you to take away from all this. This strangeness, this counterintuitive reality, it's not a failure of the universe to make sense. It's a success of human curiosity and ingenuity. We weren't given this knowledge. We earned it through observation, through experimentation, through mathematics and reason, through centuries of people asking questions and being willing to be wrong and trying again. And we're still doing it, still discovering, still being surprised. The universe is stranger than we thought. And that's wonderful, because it means there's more to learn, more to discover, more ways our intuitions will fail and we'll have to build new ones. And every time that happens, every time we uncover something that challenges what we thought we knew, we're proving something important. We're proving that understanding is possible, that the cosmos, for all its strangeness, follows rules, and those rules can be known, maybe not easily, maybe not quickly, but eventually, with enough work, with enough curiosity, with enough willingness to be proven wrong. So yes, you think you understand space. You think you know what it is, what it does, how it works. And Carl Sagan would tell you gently, kindly, but firmly that you're wrong. Not because you're stupid, not because you haven't tried, but because space is genuinely strange, genuinely counterintuitive, genuinely unlike anything your daily experience prepared you for. And that's okay. That's part of the adventure, part of what makes science beautiful. We get to be wrong and then figure out how to be less wrong. We get to challenge our assumptions and build better ones. We get to look at the universe and realize it's not what we thought. And then we get to ask, what is it really? And that question, that endless questioning, that's what Carl Sagan spent his life celebrating. That's what he wanted everyone to feel. Not shame for being wrong, but excitement for getting to discover what's right. Space is not what you think it is, but it's something better, something stranger, something more connected, more alive, and more wondrous than empty void could ever be. And now that you know that, now that you've started to see past the obvious to the reality underneath, you're part of that same tradition. That same lineage of people who looked up and asked questions and refused to accept easy answers. You're thinking like a scientist, like Carl Sagan, and that's worth celebrating.